Hello everyone. In this session, we will discuss about the high frequency analysis of BJT. In the last session, we will discuss about the small signal analysis of BJT. Here, we are high frequency signal. If we are applying input as high frequency, this frequency is very high. Then, what is the equivalent circuit diagram? What are the parameters changed? What are the parameters are introduced? And how the equivalent circuit diagram behaves. All the things will be discussed in the high frequency analysis of BJT. So this is the general biasing circuit of fixed biasing circuit. So in this already you know about the things. We are giving input and we will take the output. So VCC for the DC biasing, and this is the common emitter BJT. It has the emitter resistance and which has the bypass. CE is the bypass capacitance. Okay, we have two capacitance, CC1 and CC2. These two are the coupling capacitors which are separate for the DC and AC supply, right? And R1 R2 are the fixed biasing resistors. This is for introducing the Q point, right? So this is the complete diagram of the BJT. So here what we need to do, we need to do high frequency analysis. We need to do the high frequency analysis. So for that purpose, in high frequency analysis, two important capacitance has to be introduced. One is the capacitance between the base and collector. Why the importance capacitance will be included? Because generally in order to the capacitance will be introduced between the two conductive areas. So capacitor is the one conductive area, base is the another conductive area, emitter is the another conductive area. So here we have, look at here, in between base and collector one capacitor is introduced, and base and emitter another capacitor is introduced. Generally between capacitor and emitter is also have a capacitance, but it is negligible generally. So it is a negligible. In between capacitor and emitter also capacitance is there, but it is negligible because capacitor and emitter both having the high distance between those, so that's why it is negligible. Yes, these are the, generally these three capacitance are the stray capacitance. What is stray capacitance? Stray capacitance is nothing but, for example, if we have a conductor, for example it is a phase, it is in ground is there for transmission line, so here is the charge is there is a zero charge, so then the capacitance will be formed. This is called stray capacitance. Here also capacitor, collector is a particular voltage, base is a particular voltage, therefore a capacitance will be formed. Here also base is a particular voltage, emitter is a particular voltage, so there is a stray capacitance is formed. But in between collector and emitter there is a some distance is there, it is negligible. Okay, here what we need to do, we need to do AC analysis. We need to do the AC analysis. So you know, for AC analysis what we need to do? For AC analysis generally we have to remove, we have to short all capacitances, short coupling as well as bypass capacitors. Bypass capacitors, these two capacitors must be shorted. So these are the coupling capacitors and this is the bypass capacitors. We should remove this. And but stray capacitance must be stay in the diagram. Stray capacitance is available. What is the reason? These coupling and bypass capacitors have the capacitor's value is in microfarads, but these stray capacitors has the value of in picofarads. Picofarad in 10 power minus 12, microfarad in 10 power minus 6. That's why this affects more. The reason is here, the reason is generally capacitive impedance equal 1 by 25 Fc. 1 by 25 Fc. When F value decreases, Xc value is increases. Okay. And whenever frequency value is here, frequency value decreases, the capacitive reactance value is increases. Compare with this is more decrement. That's why it is stray capacitance is roles very important. It has a very important role. So we are doing AC analysis, but high frequency AC analysis. So for that purpose, generally we are we remove these capacitances, and if we draw the AC equivalent circuit for this circuit, the circuit is like this. So we already did in the previous case small signal analysis. In that we have the input, and R1 R2 two resistors are parallelly connected, and it is a pi network. That's why we are using the R pi, and the emitter is connected to the dielectric ground, and GM-V5 is the collector current. It's shown in the dependent current source. This is the collector element. Collector have the R0, RO. What is RO here? RO is nothing but output resistance. RC is connected to the ground only. Yeah, we did all these things, but here we have to introduce stray capacitances. Those are, the first capacitance is the capacitance between B and C. This is the capacitance between B and C. So I can write CBC. And we have the capacitance between base and emitter, that is CB. And another capacitance is there between capacitor and emitter. So that is C and E. C and E. These are the capacitances. So we can name it as like this. That name is here CBC, capacitance between base and collector. CBE, capacitance between base and emitter. CCE, capacitance between collector and emitter. These three are called as stray capacitances. So I already told, stray capacitance between nothing but the capacitance between the two potential differences. C has potential difference, B has different potential differences. Okay. So if you observe here, this is the input terminal and this is the output terminal, but CBC is connected between both input and output. So while making a model, CBC is, while making a model or while making a input impedance and output impedance, CBC makes a complexity. So just write a statement, that is CBC is in between input and output. That's why it will make complexity while making, it will make complexity while making input and output resistances, because we need to separate input and output resistances or impedances. So for that purpose we have to convert into the, by using the Millman's conversion, we will make into two different capacitances. So that's why by using Miller's theorem, by using Miller's theory, we can divide this CBC into two categories. One is CMI and another one is CMO. How CBC is this? What is CMI? Miller's input capacitance, and CMO is Miller's output capacitance. Miller's input capacitance and CMO is Miller's output capacitance. By dividing this, we can simplify the model, AC circuit model. So by using this Miller's capacitances, we can simply convert it into the AC equivalent model. That model is look like this. Just observe here, the input side CME will be added. This is the CME. So, and output side CMO will be added. Look at here, CMO will be added. And this R1, combination of R1 R2, you can name it as a RB simply, because it is connected to base. So that's why a RB will be added here. And R5 is the resistance will be added here. And we have CBE. Generally between base and emitter we have a capacitance, that is this is the CBE. And for input side we have CMI. So this is the input side CMI. And we have the another resistance CW, another capacitance CWI. What is this CWI? CWI here, CWI equal to input wire capacitance. This is input wire capacitance. Input have some connections, it consisting of the wires. So the wire also have some capacitance, that is input wire capacitance. That means generally, so we have take a wire, for example, wire inside a conductor is there, outside the insulation is there, and the capacitance between it is a conductor and it is a insulation. So for example, it is a conductor and it is a insulation. There is a capacitance will be formed. Right? So this is the input side. What about output side? So what about output side? Output side we have a resistance RO means output resistance, this is, and it has RC here. This RC is here, RC resistance, and capacitance between collector and emitter. So there is a capacitance between collector and emitter. And next CMO means we divided this Miller's concept. This is the CMO. So this value is the CMO, and this is the CWO. CWO means output wire resistance. So not resistance, capacitance. Output wire capacitance. This is the CWO. And the last part is the V0, that is the output, and starting part is the input. So this is the input side and this is the output side. Okay, input side and the output side. So this is the complete AC analysis of the, so this diagram is nothing but the complete, so high frequency equivalent circuit of BJT. High frequency equivalent circuit of BJT. That is, we have number input side having CWI, base resistance R5, CBE, CMI. Output side RO, RC, CCE, CMO, CWO. Right? So if you observe here, This complete diagram represents the input side. This is the, we can call it as input side of the equivalent circuit, and this diagram is called as the output side of the equivalent diagram. And we don't know which side we have to take the high frequency value. For that purpose we have to do some calculations, that is input side RC circuit. First you take input side RC circuit. So for input side RC circuit I can write like this. So R and C, R and C. So this is the R and this is the C. So here we can take the input voltage R and C. We can write the frequency, generally input side high frequency, FHI means input side high frequency of the AC equivalent circuit value. I can write like this, that is 1 by 2.5 RC. 1 by 2.5 RC. Here what is the R value, what is the C value? So R is, I can write like this. Here R means RB, we have two resistance RB and R5, both are in parallel. So RB parallel to R5. So this represents the R value. What is the C value? C is CWI and CBE, CMI, both are connected in parallel. So whenever capacitance connected in parallel, the total capacitance will be added. So I can write C value is nothing but CWI plus CBE plus CMI. Okay, so this is for input side of the high frequency, and we can make output side also. So I will take for output side RC circuit for high frequency. So for that purpose, here output side also we can draw like this, one R and one C. One R is there, one C is there. So here same formula, FHO, that means output side high frequency value is same, 1 by 2.5 RC. Here also observe, here we have two R's. In order to get this output side R value is RO and RC parallelly connected. So RO parallelly connected to RC. In capacitance, these three capacitance also parallelly connected. Whenever three capacitance are parallelly connected, total capacitance will be added. That's why C I can write CCE plus CMO plus CWO. So these are the input side and output side frequencies. But in this, which frequency we have to take for the difference? We have two frequencies. One is input side frequency is generated and the output side higher frequency is generated. But which we have to select here? For that purpose, better to take the minimum value of input and output frequencies. That will give a better results. Understand? So here select minimum frequency. Select minimum frequency between FHI comma FHO. So for example we have FHI value is 2 megahertz and FHO value is 1 kilohertz. So what is the higher frequency? Here the higher frequency is nothing but FHO, that is you should take the 1 kilohertz. Minimum value you should select. Okay, so this is the procedure to do the high frequency analysis for the BJT. Whenever the high frequency is entering into the system, then the stray capacitance will be entered. Frequency increases, then automatically capacitance will be introduced. Okay, this is the complete equivalent circuit of the AC analysis. So we will do the some conclusions here. So we will write some conclusions. So what are those conclusions? So here the first conclusion is design, I can write here, design value of high frequency FH using RC circuit, using RC network at input and output side of amplifier circuit. You should design first, we have to design for input and output side. And second is the higher frequency is nothing but minimum frequency between the input side frequency and the output side frequency. You will get the two frequencies, then you will select the minimum between these two frequencies. Okay, yeah. So this is about the high frequency equivalent circuit of the high frequency analysis of BJT or high frequency equivalent circuit of BJT. I hope all of you enjoyed the session. Thank you.